Okay, everybody, so I want to do a quick review with you before we take the test. So take out your review sheet, also your INB for plate tectonics and your INB for topographic maps would be helpful as well. So first of all, explain how the tectonic plates are able to move, be specific, and use correct vocabulary. So I'm looking here for the fact that we need convection currents, we have convection currents in the mantle. And when we have those convection currents in the mantle, remember our hot magma is going to rise and our cool magma is going to sink. And we have all of this going on. If this is the Earth, we've got the core here. We've got all of that going and it acts as conveyor belts to move our crusts. So when we go back here, I'm going to take and erase that so we have some room. With this, I'm going to take and make my point a little bit smaller. What type of crust is more dense? So we have our crusts on the top. So our more dense crust is going to be our oceanic crust. One tectonic plate slides beneath another at a trench. So our trenches, we need to know those are called subduction zones. Subduction zone. And that's where if you have two pieces of crust moving towards each other, this denser crust is going to subduct and go under as they meet in that particular area. The feature occurring at a divergent boundary with seafloor spreading is called a mid-ocean ridge. Mid-ocean ridge. Okay, let's see now. Note, now we're going to look at some of these pictures and you will be using each of those images more than once. So convergent boundary, that's where our plates are coming together. So D is a convergent boundary and also A is also convergent boundaries. Think come together. Divergent boundary is going to be image C. Transform is B. Boundary with a fault zone. We went over these in our plate tectonics INB, that would be B. Boundary where folded mountains occur, that's going to be D, the Himalayas. Boundary with a subduction zone. Remember, subduction zone means that you have one going under the other, so that is going to be A. Boundary with the formation of an island arc. This is one of those crustal features. It's going to be a convergent boundary, A, and remember, these are going to end up being volcanoes that form. And so if this is an ocean plate and an ocean plate, those volcanoes will end up being islands, okay, in this particular case. Get rid of that. Boundary with a formation of a rift valley. That is going to be C, going apart. If these are both continental crusts, then you're going to get a rift valley. If they're oceanic crust, you're going to get something else. Boundary with seafloor spreading. That is also going to be image C. Oops, don't know what happened there. But yes, I am filming. So in boundary here, boundary with seafloor spreading, these are two ocean plates right there. And so that is also going to be image C. The next one, boundary with slipping, tension, and earthquakes. It's going to be B. I think of the St. Andreas Fault. Boundary with crust melting into magma in the mantle. That's going to be A, because remember, as this subducts and goes down, we've got our mantle. It's going to be really hot. Boundary with a trench. That is also going to be A. Remember, associate subduction with trenches. You're going to always have a trench formed right here where that subduction happens. Number 17, boundary with will most likely lead to volcano formation. That is also going to be A. Anytime you get subduction, you're going to get volcanoes formed. And boundary at which new crust is being formed. That's going to be, if we're making new crust, that's going to be C, because this is where we're going to have magma coming up, cooling and hardening, especially ocean to ocean when they're moving apart and we get seafloor spreading. Okay, What is the continental drift theory and who came up with that? What is Pangaea? Well, Pangaea was the idea that Alfred Wegener, Wegener, thought that all the continents were once connected in one large landmass called Pangaea, and then they have drifted apart to their current locations. And the force or the engine that powered that movement, another guy came up with once we discovered that in our mantle, we have convection currents. Convection currents. What is the theory of seafloor spreading and who came up with this theory? Why is it important? Well, seafloor spreading, we had a guy named Harry Hess, and he found out that we had these mid-ocean ridges in the bottom of the ocean where we were having divergent boundaries and we were getting new seafloor. And it's important because now we know why Wegener's idea of the continents moving could happen, because Wegener didn't know how it happened. He just thought because of fossils and everything that it had. Okay, let's go over to our next page. After we did theory of plate tectonics in terms of plate boundaries, we moved over to topographic maps. So what's a contour line? A contour line is, let me change my color pen here. A contour line is a line of equal elevation. So you're going to have the same elevation. So if we have this line right here that all along that area, it has the same elevation. So you're going to have all these squiggly lines there. What is the contour interval on the map shown? Well, the contour interval, I will tell you, even on your test, I believe it's going to tell you the contour interval there. So that is 20 meters. What do very close contour lines on a topographic map indicate? Well, if they're close together, like in this little area here, that's going to mean very steep elevation, a steep elevation. And when they're far apart, it's going to be more flat on there. It's going to be flat or not as steep. What is the change in elevation between the two locations shown as black dots? Well, if I know my contour interval is 20, this says 500, this says 600, so I know I'm going uphill, I need to add. So this is going to be 520, and this one would be 540. And then if I go over here, this line is on this one, so I can go, okay, that's 620, 40, 660. This is 660. So the change in elevation, I'm going to take 660 and subtract 520, and I'm going to get, is that right? Oh, not 520, 540, sorry. I'm going to get 120 meters, because that's my unit that they gave me. Okay, let's go to our next one. Now we have a contour interval of 10 feet. What do the V-shaped contour lines on the map above indicate? Well, remember we learned before spring break that V-shapes are going to be valleys. Valleys. And I can see that I have some tall hills, tall hill, tall hilltop, and I have these V-shapes right here. So these are my valley areas. And the fact that there's a stream or a river running through there indicates that. What does the triangle at 533 mean on Aurora Hill? That's the actual elevation. It's not on a contour line, but that's the actual elevation at the highest point. And then describe how the contour lines would change if Colden Creek erodes more land over thousands of years. So here's Colden Creek. If we have more erosion, we're going to get steeper V's. So we would get steeper V shapes with that. All right. Let's now go to our next. Now we're going to look at our satellite images. Now, I was actually confused on the black and white version. I didn't know what the years were because you couldn't see in color, but this actual outside line is the current beach line. So this was back in 1943, 55, 67. So this coastline and beach has changed over the years. Predict what it might look like in 20 years. Well, I would predict that we would have even more land out there. So it would deposit more land. Deposit more land or soil. Number 9, this dry, arid means dry, crater in Arizona will experience wind erosion. What do you think will happen to its steep-edged rim? Well, do you see any? If it's dry and arid in Arizona, there's not a lot of vegetation or roots to hold the soil in place. So when the wind blows, maybe it's not steep. So I predict the wind will blow some of the soil into, and it will not be as steep. So maybe it would round the edge a little bit and it wouldn't be as steep. Not as steep. Boy, my handwriting is really bad with this. Okay, now here's an example of when we did them in class, they were in color. This is where you're going to have to look at labels. See, it says Pacific Ocean and there's Inland Bay. Remember, bay means no waves, okay? Which areas of the coastline are more likely to experience the greatest effect of erosion from waves over time? Think about the pounding ocean waves day after day. Well, N is pointing inside here on the land, looking in the bay area. P is really inside, almost on the land. S is right here kind of at the inlet into the bay by the ocean, and T is kind of on this inside area of the bay. So we know bays don't have as many waves, the outside does, so S would be our area that would have the most erosion. All right, let's go now to this. Describe the benefits of using satellite views before and after natural disasters and understanding the effects of erosion. This just actually allows us to see visually what's happening to compare. So then maybe we could put things in place to protect from natural disasters and to protect people's homes and things. You can tell in this bottom picture here that a lot of the homes were flooded and destroyed. Okay, let's go do some more work on topographic maps. We've got point W and point Y, and we've got a couple families that are hiking to X, which is at the top. The question says, what is the change in elevation to the nearest 10 meters? Well, let's see. My contour interval is 20, so that's based on tens. For the family that took the steepest path to point X. So we've got to figure out which family had the steepest path, W to X or Y to X. So we've got to think lines are close together. So this one over here, the Y to X, their contour lines are close together. So that's the one we need to figure out. And then you're going to find the elevation for the family and subtract it from 600. So contour interval of 20. This is 500, 440, so this would be 460, 480 here. And so I would take 480, and I would take and subtract that from 600. So that's going to be 120. So remember, when you fill it in online, you put 120 if you're doing online. And then if you had to bubble, this is what you would do. You don't have to put the leading or lagging zeros there. Okay, let's go to this last page pretty quickly. How would tectonic maps change how would topographic map change if tectonic activity were occurring? So we're talking mountain building. Maybe we would get an extra contour line at the top of a mountain if it was increasing in height. How would a topographic map change if weathering and erosion were occurring? Well, maybe the area of the beach, the 0 meters above sea level might change their shape a little bit. Maybe the V shapes would change in valleys. When information is obtained from a satellite image, we can see if there are plants growing, we can see water features, we could see buildings and those kind of things there. We could also see the land, obviously. Okay, what information is obtained using a topo map? When would it be best to use a topo map? So topo maps are going to always tell us elevation. And when would it be best to use a topo map? Anytime you're building or constructing something, planning, architecture, engineering for roads, and that kind of thing. Okay, now here's where we need to know our important places on a map. Label number 1 on the map where 2 continental plates move towards each other. Well, our famous one we learned is right here, the Himalayan mountains, and that's the Indian plate and the Eurasian plate. So this would be your number 1. You're going to get tall folded mountains. Number 2 is going to be where they slide and grind on each other. What's the name of the boundary? That's going to be over here in California. So this is my number 2 over here. That's a transform boundary. You're going to get earthquakes at the